When you look up, you might think you're staring into an empty void. In reality, you are sitting at the very bottom of a massive, heavy ocean of gas, pinned tight to the planet by gravity. This fluid ocean is composed almost entirely of two elements, about 78% nitrogen and 21% oxygen, and its density drops drastically the higher up you swim. This diagram maps out the layers of our atmosphere, tracking the wild temperature variations from the surface all the way to outer space. This layered structure acts as a vital shield. It intercepts and processes solar radiation and cosmic debris long before it can reach the surface. In the middle layers, the stratosphere uses ozone to filter ultraviolet rays, while the mesosphere acts as a physical barrier, burning up incoming meteors. Higher still, the thermosphere reflects radio waves and hosts the glowing electrical interactions we call auroras, before finally fading out into the thin exosphere. But all the action that actually dictates our daily lives happens in the bottom 12 kilometers, the troposphere. Down here, the air exerts massive pressure on our bodies and traps nearly all of the planet's water vapor. Unlike the quiet, protective shields above, the troposphere is violently and constantly churning. So what is the invisible force pushing millions of tons of this air around the globe? This diagram shows incoming solar energy, or insolation, feeding the Earth. Because our planet is curved, that sunlight strikes the surface unevenly. That uneven angle creates distinct temperature bands across the globe, from the intense heat of the torrid zone at the equator, grading down to the freezing frigid zones at the poles. This uneven heating kicks off the core physics of air pressure. When air heats up, it expands and rises, creating a void, or a low-pressure zone. Conversely, cold air is dense and heavy, so it sinks, creating a high-pressure zone. Nature hates an empty void. To balance the scale, dense air will always violently rush from a high-pressure area into a low-pressure area. That simple act of the universe trying to balance high and low pressure is the sole reason wind exists on Earth. To see this in action, you just have to visit a local beach. Land heats up and cools down much faster than ocean water. At night, the sand cools rapidly, creating a heavy high-pressure zone over the shore. Meanwhile, the ocean retains its warmth from the day, creating a rising low-pressure zone over the water. To fill that void, the dense air rushes from the land out toward the sea. We experience this physical balancing act as a gentle nighttime land breeze. That local breeze is a small-scale thermodynamic engine, processing the sun's uneven energy right in front of you. Now, take the exact same physics from that beach and scale it up to cover the entire Indian subcontinent. During the summer, the massive Indian landmass heats up much faster than the surrounding Indian Ocean. This opens up a colossal low-pressure void stretching across the entire continent. To fill that void, high-pressure, moisture-heavy air from the ocean violently rushes inland from June to September. This is the advancing summer monsoon. It brings torrential, life-giving rain that saturates the soil and sustains the continent's agriculture. Then, in October, the cycle reverses. The land cools rapidly, returning to high pressure, while the ocean stays warm. The dense, dry wind turns around and blows back out to sea. The massive, continent-defining Indian monsoon is driven by the exact same physics as a quiet evening beach breeze. Because this thermodynamic engine dictates the supply of food and water, human civilization has obsessively tracked its rhythms for millennia. Ancient Indian scholars used solar positions and nakshatras, lunar mansions that divide the sky along the moon's path, to predict these vital pressure shifts and prepare for the seasonal rains. Today, modern meteorologists rely on advanced climate models to track these exact same invisible forces, securing food production and protecting human life. The atmosphere acts as a massive, living thermodynamic machine. Its rhythmic breathing makes life on Earth possible.